Hello. I'm going to present the paper Asymptotic Behavioral Sequence Models by Flavio Chierichetti, Ravi, Kumar, and Andrew Tomkins. This paper deals with online sequences. For instance, the sequence of videos you consume on YouTube, or the sequence of URLs you consume by browsing the web, or maybe the sequence of songs that you consume on Spotify. On each of these services, you have a sequence of tokens you consume. And maybe there's a fixed history composed of three positions or three slots containing the tokens A, B, and C. Whenever you are about, or the user in our model is about to consume a new token, the user takes a look at all the previous slots, right? And selects one of these slots at random. Maybe the user would select slot 2, and in which case it would copy B from slot 2 to the next slot, or the user will be selecting slot 1, copying A to position 4. Then the user moves on to the next slot, and again, it will consider all the previous slots and will be copying from one of them at random. Maybe the user will be copying from slot 2, and so a B will end up in position 5. The user moves on again, selects again randomly a previous slot, copying from that slot whatever the user finds in that slot. So for instance, if the user selects slots 4, then slot 6 will contain token A. And observe that slot 6 contains token A not only because A was in position 1 in the history, but also because A was copied in position 4 because of what the user selected when it was about to choose what to put in slot 4. So in other words, we get A in slot 6 because there's a walk of length 2 ending up in position 1 in the history. And the walk from position 5 has only length 1 and ends up on a B. Then the user will move on to maybe slot 7, copying maybe directly from the history or maybe not. And in general, when the user is about to select one of the previous slots randomly, it does so according to a set of weights. We assume to have an infinite sequence of weights, maybe monotonically decreasing, all non-negative, and the user, when in position I, copies what's in position I minus k with probability proportional to wk. So the user will copy from the last field slot with probability proportional to W1, second to last slot with probability proportional to W2, and so on and so forth. A particularly relevant case is the case where Wi is equal to I to the minus alpha for some alpha greater than 0, so the power law case. The power law case is interesting because Anderson et al. In WWW2020 introduced this model and observed that this weighting sequence followed a power law with exponents changing from setting to setting. And so in our paper, we study the asymptotic behavior of this process, particularly in the case where the WIs follow a power law. Now we'll be defining precisely the problem that we aim to solve. Suppose that we're given a set S of tokens, videos, songs, or URLs, and let sigma be a sequence of the elements from this set. So maybe the set contains tokens A and B, and sigma is composed of A, B, and A. Then this ABA will make up the history from which the process will be run. Then we start the process starting from that history sigma, and the type of question we ask is, how often will each of the tokens from the set be consumed by this random user? In the case, say, of Spotify, this question corresponds to how many times will the user listen to a given song, or in the case of YouTube, how many times will this user look at a given video. Now, clearly, this number of times depends on the random choices made by the user. So maybe if you run the process once, we will end up with lots of A's and few B's. And if you run it a second time, we will end up with lots of B's and maybe few A's. So the vector of fractional consumption will actually be a random variable whose distribution depends on the history sigma and clearly on the WIs. In the example we see at the top of the slide, the user has consumed lots of B's and few A's, and therefore the vector will be tilted toward the B axis. If instead, maybe the user downloaded lots of A's and few B's, then this vector of final consumptions will be tilted toward the A axis. So that's the problem we care about, and now let me tell you a little bit about our results. So suppose that the WIs follow the power law observed by Anderson et al. And suppose that alpha, the exponent of the power law, is less than 1. Then we show that the vector of fractional consumptions converges to a random limit on the full simplex. This limit will be random, so maybe sometimes it will be some point, and some other times it will be some other point. But it will be convergence to a final point if alpha is at most 1. If alpha is more than 2, then with probability 1, a single token will make up a 1 minus mod of 1 fraction of all the consumptions. That is, again, we have convergence to a limit, and this limit will be of a very special form. It will be some vertex of the n-dimensional simplex. So now let me tell you a little bit about our analysis for the full simplex case, so for alpha at most 1. The analysis leverages on what we call the vanishing collision probability property of our process. What's this property? So fix a history of length h and consider the walks ending in the history starting from two positions I and j that are far enough from each other on the line. So maybe look at position I on the line and consider the walk that goes from I to the first position in the history, and do the same from j. We show that the probability that these two walks merge in a position outside the history converges to 0 as h increases. So given this property, which by the way holds in a more general case than the power law case, we prove that the process converges to a random limit. So given this property, the process has to converge to a random limit. Moreover, our analysis does show concentration. We show that as time progresses, we get closer and closer to the final limit. So maybe at the beginning, we have this red point representing the expectation of the final limit, and we know that there's an area of a given radius around this expectation where the final limit will end up in with high probability. As time progresses, maybe the expectation moves around a bit, but the area shrinks, the radius of the area shrinks, and becomes smaller and smaller, converging to 0. Now for the single token case, that is alpha more than 2, we show that with probability 1, there will be some position t such that no later position will copy from before t. In other words, position t will sort of act as a wall, forcing each subsequent position to end up in t itself. This implies that whichever token is in t, that particular token will be copied over and over again up until infinity, starting from t. Now let me show you the results of 2 runs of the process. In the first run, we selected 2 tokens, A and B, and we set alpha equal to 1/2. We ran the process for 100 times, making up the history. Then, having fixed this history, we rerun the process starting from that same history over and over again to get a distribution on the fraction of consumptions on item A in the first 1000 steps, say. You see that the distribution of consumptions of A follow a Gaussian-like variable centered around the expectation given by that particular history. If we were to run the same process but with an history of 1000 steps and maybe run it over and over again up until 10,000 steps, we get again a Gaussian-like variable with a much smaller standard deviation, confirming our concentration result. So see the paper if you're interested in this for more details. We do have some preliminary results for alpha bounded between 1 and 2. We also have a bunch of open questions that revolve around generalizations of the model. For instance, what happens in a modified process where instead of a linear normalization of the weights, one applies a softmax-like normalization? Also, can one generalize the process and the analysis to the case where the probability of copying from a position also depends on the user context and whichever token is in particular position? Thank you very much for your attention.